Hello, this is a review and teardown of an eBay DC motor speed controller. This is the first video that I've tried to edit properly, so please let me know what you think in the comments, how I can improve, and if you'd like to see more of the same or something different. So today I wanted to do a teardown of this motor speed controller from eBay. I'll go into the details of why I bought it and what I need it to do, and we'll see if we think it can do what it says on the tin. So hopefully, as you can see here, this is the motor that I need to control. So this is, I think, out of maybe an electric lawnmower or possibly a mobility scooter. I think, if I remember correctly, I mean this was possibly as long as 20 years ago that we bought and fitted this motor. But I think it was maybe 24 volts, if not then it's definitely 12 volts, and it's fitted to this kid's Jeep that my dad actually built, and this has got the motor installed in the back, driving one of the rear wheels I think, and then it's got a forward reverse direction control as like a gear lever, and an accelerator pedal down there, and then a 12 volt battery in the front. So it does already work, but what we wanted to do was be able to control the speed of the motor so that my nephew can use it without sort of steaming off into the distance and crashing into something, and maybe as well make it remote control. So I went looking on eBay for a suitable speed controller, and I came across this one. Apparently DC 10 to 55 volts, max 60 amps, PWM motor speed controller, clockwise, counterclockwise, reversible, switch, don't know what that means, 12, 24, 36 volts. Guess it's, yeah, I mean, should be compatible with those. So you can see here, the reason I picked this one was because it came with it kind of comes in a case. Some of them are just a PCB, so that's a bit easier to mount. It comes with a fan. It's got the speed controller, it's got the display, and forward reverse switch. Most of them pretty much do the same thing. But yeah, according to the, well, I would hesitate to call it a spec sheet, but the eBay listing at least, it's long service life, support large current start, protection for motor stall. So I think that's a good thing, because I suspect that this motor, the stall current could be 100 or 200 amps. You can see it's got some pretty beefy solenoids on the top here. I think these are actually 4-pole solenoids, and they're used for controlling the forward reverse function on the motor. They're probably like 100 amp solenoids, maybe 200 amp solenoids. They're similar to what you'd find on a car starter motor. So as I say, they're obviously designed for switching full power. Yeah. So if the motor's potentially at stall, they'll still switch it on and off. Yeah, but I think this motor would probably draw maybe 40 or 50 amps at kind of peak power, continuous. So this claims, to be a 60 amp here, but then it says 40 amp here, so who knows, I guess 60 is maybe peak and 40 is continuous. Built-in heat dissipating fan, not easy to fever. Good news. Digital LED display of 0 to 100%. Fine workmanship and good performance. That's what we like to hear. Okay, so it's you can see here it's a 15 centimeter ruler. Yeah, 12 by 9 centimeters. 10 to 55 volts, equal to the rated voltage of the motor. Linear output under load control. Linear output under load. There's the output voltage. Max output current 60 amps, continuous current 40 amps, speed range 0 to 100%, reversible switch, clockwise, counterclockwise, speed regulation mode, potentiometer 100k with switch function. So I wasn't actually really sure what that meant, but we'll see in a second. And speed regulation type is regulating current. And I kind of took that as a good thing, because I thought potentially if it's capable of actually controlling the current, then it may be able to essentially reduce the speed or reduce the voltage in order to regulate the current under the max current. So there we go. So I bought that. I don't know, came like within 2 days. It was £12. I thought I couldn't really go too far wrong unless it catches fire. And here it is. So you can see on the front here you've got the kind of off 3-position switch, off, and then I assume forward and reverse. Okay, great. Display, I couldn't understand from the listing what the display would actually do, but you'll see in a second. And then potentiometer. Now the potentiometer has that's fully off. It's got a switch for the first sort of switch detent for the first part of the rotation, and then a kind of 1-turn pot. So that's the speed control. Okay, so I've already taken the case off of this because it was a bit tricky to get off. There we go. Okay, so let's just zoom in a bit there. Alright, so let's see if we can get the board out. So I'll disconnect the fan first. It's quite nice actually that it's got connectors on rather than being soldered straight to the board. Sometimes they'll be soldered straight to the board. You can see here this connector for the screen, which is kind of a bit useless being so short, but the pins are all bent over. It doesn't look great, and I think that's just because the way the case fits on, the pins kind of stick out the front of the case. I guess this was originally designed to have the screen mounted directly on here, but to be honest, it really doesn't work that well. Anyway, okay, so the other thing to note that I thought was a little bit concerning was the size of these terminals. So if you look at the size of the terminals on this motor, you know, that's I think that's an M8 possibly, and well, the terminal won't even physically fit on here, but you know, they're that size for a reason. They're obviously supposed to carry a fair amount of current. Now if you look at the smallest wire we've got on there, this one here, I guess that's like a 4mm maybe, and these are probably 6mm wires. I don't know what that is in AWG, I'm afraid, but so clearly this has been running for a reasonable amount of time, and clearly that wire there at least has been able to handle the current. Now this one does look like it's had some damage, but that's probably more chafing on something. Maybe it's shorted out on the case as well at some point, but I don't think that's because of current carrying capability. So yeah, anyway, the size of these terminals are the first clue that this may not be able to handle the current you might expect. Okay, so then the case kind of basically has the board slotted into it. It kind of gets stuck down here because the solder joints are too close to the edge, so they get caught on the plastic, but there we go, it comes out fairly easily. And you've got a fan mounted in there. That's a 12-volt fan, Chinese brand, but you know, it's what you'd expect. Brushless DC, that just pops out like that. So yeah, that is good that it's got a fan at least, so you know. And then that's the board. So there's obviously a number of different electrical topologies that you can use to control a DC motor. The one that you'll find on kind of the smaller boards that you get for Arduinos, I don't know if I've got any around here, but are what they call an H-bridge. So in an H-bridge, what you would typically have is you'd have your motor here, and then, I mean, because it's a DC motor, there's not really a positive and negative, it'll run either way in theory. And you'd have your power supply here, so you'd have, say, plus 12 volts up here, and you'd have your negative here, or your ground down here. And then in order to supply your motor, you have basically, I'm just going to draw them as switches like this. Oops. Apologies, terrible drawing. You would have an arrangement like this basically. And so if you want to run your motor in one direction, you close this switch and this switch, and the current will flow through here, through the motor, through here to your battery negative. You could draw a battery here. And if you want to run the motor in the other direction, then you open this switch, you open this switch, you close this switch, you close this switch, and current will now flow through here, through here, through the motor in the opposite direction, through here to ground. And so that enables you to drive the motor in both directions. And that's actually what the solenoids on the top of the motor here are doing. They're basically opening and closing those contacts in order to drive the motors in both directions. Now you can do that either with physical solenoids, or you can do it with transistors. So maybe instead you might have, okay, so you'd have your transistors there. And in this case you electronically switch these instead of kind of like on a, if these were relays or solenoids, then you'd have a big coil on here, and you'd switch the coil using some switching mechanism in order to close this. In this case you use an electrical current to close the transistor essentially. That causes it to conduct, and you can kind of do the same thing. Now if this motor was really small, say maybe less than, I don't know, 100 milliamps, then these could be potentially transistors. But if you want to go bigger than 100 milliamps, say, I don't know, just roughly, then you're going to need these to be MOSFETs instead probably, or potentially other high current switching devices like IGBTs. Okay, so what you'll find in the boards that like the Arduino shields is typically this setup, all in kind of a, they're typically in a driver chip called an L, let's call an L, I don't know, 18 something. And that's basically all of this contained within a chip, and they're basically, I think they're very low current MOSFETs, and they'll drive up to maybe 2 amps say. Then when you get a bit higher current, if you want to go say between 2 to, well, there isn't necessarily a limit, but I don't know, you end up with different topologies. So anything higher than 2 amps, you're typically going to not be able to get it all in one chip, but what you end up with is something that looks a bit like this, and you might have transistors, not transistors, they'll be MOSFETs, which are these MOSFETs here, and you'll get they'll come mounted on a PCB. So you know you may have something that looks like that on a PCB, and it'll have very similar to this heat sinks with transistors on, or MOSFETs on, and what they'll be doing is switching the current like this. And then if you need to control the speed, you can essentially put a PWM signal on one of these, and what they'll do is it essentially turns the motor on off on off on off on off, but so quickly that the motor just basically it filters that, and instead of seeing a voltage that's maybe like 12 volts, if you do a 50% duty cycle, you'll get a voltage that's effectively 6 volts. Okay, and you can do that by switching either the transistors, the MOSFETs or IGBTs on and off very quickly. Now, kind of strangely, this board has some sort of combination of the two setups that we've got here, because it appears to have two large relays on it. Now, what I might just do here is give this a black background. Yeah. So this board seems to have two large relays. Now they're not huge. They look like the sort of relay that you, like a normal 12 volt automotive relay. Probably, well, typically they'll be rated for 20 amps. For a smaller one, probably. These look like maybe 40 amps, possibly 60, but not really anymore. They don't actually have anything written on them, so I can't tell. You can see the contacts there. And then also you've got 1, 2, 3, 4, 5 chips of some sort, which are clearly used. They're clearly high power semiconductor switching devices of some sort, and we'll look at what they are in a moment. So that suggests to me that this is some kind of hybrid topology where you've got by the looks of it, possibly relay coils here which are performing the actual current switching for the motor direction, but maybe we've got the capability here to because what we still need to do is to control the speed of the motor, we need to produce a PWM signal. So going into the motor, we need to be able to produce this kind of on-off signal, and you can't do that with relays or solenoids because they can't switch fast enough. I mean, you could do it, but they won't last very long, because every time you open this switch, you get an arc here when you open the switch, and that causes the contacts to get hot and eventually they'll melt. So you can't do it with relays. So you can close these relays once, dunk, turn them, and that'll start the motor running. But if you want to be able to control the speed, you need to be able to generate this signal here. And there is a way of doing that in this kind of setup, and you could do it instead of at this point or this point, you could do it up here. So you actually have another switch effectively, or we'll draw it this time as a transistor. I would draw a MOSFET if I could remember how to draw one, and effectively this generates the PWM signal here, which then gets fed through the circuit to the motor. Okay, so possibly that's what's happening here. And in order to get the current capability, what you could do, although I'm not convinced it would work very well, is essentially have, I don't know how to draw this now, but you essentially have a load of parallel MOSFETs. So maybe I'm going to draw the 4 there, if there's 4. That's really bad drawing, sorry. But and then, you know, each one of these shares the current, so the current carrying capability of one individual one wouldn't need to be would be 4 times less. So that's possibly what's happening, because I think it must be, because I'm not sure what else these relays would be doing if that was not the case. Anyway, so going to look at the board itself, we can start to get some clues. So firstly, let's look at the controls. So we've got the forward reverse switch, that's just on a plug here. And yeah, I haven't reverse engineered the whole diagram, the whole circuit, but I think that simply goes into these relays. So I think that all that's doing is switching the direction of the relays, or with the middle position, it opens them, so they'll be double pole, double throw, I think. Then on the board, well, then we have, yeah, for the speed potentiometer, we've got the switch and the potentiometer, which you can actually see is two separate plugs, and it's two separate contacts on the potentiometer. So the switch is these ones, that's this plug here, and the potentiometer controller is these ones here, which is good because we can potentially wire this so that the throttle pedal's attached here, the gear select lever on the Jeep is attached here, and then the potentiometer remains attached here, and we have control of that, maybe via a remote control or something. You've got the fan plug there, and then you've got some chips. So this chip doesn't have anything on it, but this is kind of probably the control chip for the speed control maybe, and it displays on the, it drives the LEDs on the display. And then you've got, this is a voltage regulator, this is a 555 timer. Let's just make sure we're zoomed in, yes. And this is another voltage regulator. So this one's actually a DC-DC converter, and then that's a voltage regulator. And the chips here, the drivers, this one appears to be effectively a rectifier, so it's two diodes pointing at each other with a single output. So that's like, it's even drawn on the chip what it looks like. It looks like that. So if you try and flow current down here, it will flow through here and then out here. If you flow current through here, it will flow out here. But if you try and flow current up here, it will be blocked by these two diodes, so you won't get any flow out here. Okay, so this is yeah, like would probably be normally used in rectifying, where you're not necessarily sure where, or you could have current flowing from either of these two, but you don't want it flowing backwards. Or this is used for reverse polarity protection potentially. And I think it's connected, yeah, I'm not sure, I'd have to draw the circuit diagram to work that out. And then you've got 4 MOSFETs. So those MOSFETs are P75NF750ST, and I suspect they're reclaimed off of something, because that's probably better lighting, because they seem to have a lot of solder up the legs. The legs are slightly different lengths, and the kind of, it's hard to see now, but the colour and the wear on them looks different. Like some of these look a bit more corroded than others, but there we go, that's to be expected. And then they've each got aluminium heat sinks, which are actually staked in, probably can't really see it, maybe you can see it through there, I don't know. They're actually staked into the PCB, soldered into the PCB there, which is quite good. We've got some smoothing capacitors. They're just I think directly across the motor. Oh, I've just thought maybe what this is the flyback diode, protection diode. It could easily be that. So what that would be is basically when you're running your motor and you want to stop it, there's lots of energy stored up in here essentially in the windings in the coils, and also because of kinetic energy it's rotating. When you open these switches, that energy has to go somewhere, and what it'll do is you're no longer providing power to the motor, but the motor's still spinning, so it will become a generator, and it will actually provide current and try and get through those switches that you're just opening. And that's why I was talking about this arcing here. So it will actually force current through the switch as it starts to open by creating an arc, and that will quickly destroy your switching mechanisms, and especially for semiconductor switches. And what we're saying is that when your motor's spinning and you open one of these switches, the inductive energy in the motor and the kinetic energy will essentially try and continue to allow that current to flow, which creates an arc here. And the way that you need to stop it is with flyback diodes. Now normally in this configuration of H bridge, so this is an H bridge. In this configuration, the way that we would arrange our flyback diodes so that we don't have that problem is by placing them essentially over the switches, like so. And so what that will do is when the battery here again, when the motor, when you've opened all these switches, there's still actually a current path to flow. So the motor, if it's trying to flow current, say out of this, so in that direction through the motor, then it'll be able to flow up here, through here, and back into the battery, and closing the circuit out through this way. If it's trying to flow in the opposite direction, then it will be able to flow up here and into the battery, and likewise. And that actually also allows for regenerative braking, because if this motor is being driven by something, then you've always got that current flow path back into the battery, so you can regenerate. And there are some other sort of odd things that you can do with the motor. So if you want it to brake, then you can actually close this and this switch, and then you're essentially shorting the motor windings themselves, which will tend to cause the rotor to brake, essentially to stop. Okay, so on this board, however, because we've got some sort of hybrid between like a relay and transistorized H bridge, I'm not entirely, and there only appears to be one of these diodes. I think there's something else slightly different going on, but off the top of my head I can't quite work that out now. So what else I wanted to show was the data sheet for the P75 NF750, and okay, so this is essentially we want to check, you know, do these components really, do we think they'll stand up to the abuse we're going to give them? So you can see here, well, we've got some general features, starting features. So these are in the TO220 package. It's the metal tab on the back there rather than the plastic package, and not the surface mount. And there you go, there's the diagram of how to draw a MOSFET. So VDSS, the maximum from the source here to the drain here. RDS, on, that's a really important number, so that's the resistance from the drain to the source, so from here to here, when the MOSFET is on, in the on state. And it's less than 0.011 ohms. And maybe we'll come on to why that's important in a minute, but you can imagine that the higher the resistance through here, then when you're conducting current through here, if this is a higher resistance, you will generate more heat, and heat is the enemy of these. Okay, and then ID, so current at the drain, so that's current through here, maximum limit 80 amps. Well, so that sounds promising. You know, it's suggesting, and I think the 75 number in there is related to the current, suggesting this is capable of 80 amps. Now, 80 amps is an awful lot, actually. So, you know, it's if you look at even these pins, do you really think we can pull 80 amps through one of those pins? Well, maybe. On although we can also bear in mind that, as it states here, D, the drain, which is the drain current as well, is either pin 2, so that's the middle pin there, or the tab. So the tab is the back part here. So obviously we can conduct drain current through the tab here, then through the heatsink, so long as they're connected, which they're not always, because sometimes you'll have a electrically insulating, thermally conductive barrier in there for good reasons. But and then of course it'll only conduct if that heat shield is connected to one of the traces on the PCB. So we can see on the back here it's not on any of those, but it might be on the front. So we could probably check that. Well, we can check that because we've got a multimeter. So is it connected? Yep. Oh no, not that one. So that one's not. But they are all connected, and they are connected to none of those. Surprising. I would have expected it to be connected to one of the outputs. The motor. Ah no, it's going to be going into one of these relays, because I think those MOSFETs essentially are some sort of, I'm going to draw it as a black box here. So they're not, the drain, which is probably going to be this part of the circuit here, is not going to be connected to an output directly, but it'll be connected through one of the relays. So we can check that. Let's see. Yep. So it's that pin on the relay. And these are probably ISO standard relays, so we can look up, you know, this looks like an automotive relay. I think they're typically the coil, that's the center contact, and then it switches either the center contact either to this pin or to this pin. So if this was the coil, we would expect to see some resistance across there. So let's go to resistance. So we see, yeah, 80 ohms, that sounds about right for a coil. And then we'll have a normally open and a normally closed contact on here. So that's megohms, that's not connected. And through here, 0 ohms. So that's the normally closed contact. And that would be the normally open contact. Okay, so just coming back to here, this is connected to, put that on beep, the normally open contact. Just looking at the PCB a bit more, so there's some, don't know if you can see that, but there's some kind of like, I don't know, like water damage on this maybe. It's not conformally coated. It's not the, you know, it's not been treated very nicely. There's definitely some water damage on there, but otherwise the soldering's all pretty good. There's no dry joints as far as I can tell, and they've increased the current carrying capability of the power traces with these additional solder covered tracks. It's kind of odd, I think. I don't know, I guess somebody would probably be able to tell me why it's like this, but I would kind of expect these to be joined up and in a straight line, for example, but perhaps this has been done through some kind of computerized optimization process where it's calculated where the high current flow path in the trace is, because if you've got a flat trace, so like this is the ground plane, the current kind of doesn't flow equally in the whole thing. If you've got two high power current points, so say you've got current going from here to here, then the current's not going to flow up here and around here or equally across the whole thing. It's going to flow directly from there to there, and it'll kind of, I guess, it'll have some sort of field almost around it, which will be the current flow path. So you can see probably, you know, the output is here, so this is to the motor. High current flow is going to be going, you know, down this trace in this direction, so you can see why they've got that one there. Now what we can do is look at the PCB trace width and see whether we think that would be capable of carrying the current that we're talking about. So that's only 8.5, 8.5 mil. Yeah, that's probably the narrowest bit. So 8.5 millimeters. Now we know that this has got the kind of increased track there, but to be honest, it's not very thick. You can get PCBs with different thickness copper, but this is going to be the standard thickness, so it's not going to be anything thicker. I'm pretty sure, because it gets pretty expensive, and it's easier just to run these 1 ounce. Then that's probably what this board is, and that comes out at 24 amps. We double that, 35 amps. Yeah, okay, maybe. But that's still with a 45-degree temperature rise, so I don't know, it seems like it's pushing it. So, yeah, I could go into more detail on the MOSFET characteristics and calculations, but maybe I'll do that in another video. So what I did want to do was actually test this. So what we've got here is a fan. I've got a big fan off of my MR2, the intercooler fan. It's yeah, I mean, I've only got a small power supply, so I'm not going to be able to drive it to full current. I'll have to leave that test for another day. But essentially, if I wire this up, so we've got motor positive. I mean, it doesn't matter because we drive it both ways. Stick that in there, and the other motor connection in there. The terminals are fairly nice, I suppose, and if you had ring connectors on the wires, then they'd be reasonable. Although, like I say, probably not as big as I would like to see. And then if we connect, if we connect up power to here and here, here and here. Not the best way to do it, but there we go, right. Okay, we'll put that in the, so we'll set the potentiometer off, we'll set the switch to the center position, turn the power supply on. Power supply is set to 14 volts. Let's get the fan, so the fan's over here, we'll put that in there and connect the fan. Okay. Power cable's come off. Oops. Right. So now we can set a direction. Doesn't do anything. No display at the moment. So let's see. Zoom this out a bit. Okay, no display. We can change the direction, but it's not doing anything to the board. I think the board is completely off. I measured it earlier, it's drawing I think 8 microamps in this state, and that's because the main power switch is on the potentiometer here. So as we click the potentiometer on, hopefully you can see the display comes on, and it's reading 000. Okay, if we ramp the potentiometer up, we can go from 0 to 100 as a percentage, basically, that's it, full, and back down. Okay, and then we'll set that to, well, we'll set it to 0, so that's no motor output, but the board's now powered on. The fan's spinning on the controller, and then if we set a direction, so we set here, now that, just click the relays over. If we go the other way, we can hear the relays changing over. Now the output motor is not spinning yet. Let's just see if we can bring that into shot. There we go. So hopefully you can see that. This little fan here sort of sounds like it's taking off. Okay, we're drawing 0.28 amps at the moment, 280 milliamps. And I think that's just for running that fan basically, because there's no output going to here. We can actually check the voltage going to the motor. There may be some output to the motor, possibly. The measure across the motor terminals, 0 volts. Then if we take the motor output up, yeah, you can see that comes just off of the stop there. We move it ever so slightly. Yeah, and then there it starts at 0.16 volts. The current's not gone up from the power supply yet. As we increase this, the current increases. So let's see, and the motor starts turning about 1 volt. And we're now drawing 310 milliamps from the power supply. So we can ramp that up to the full. I've got the power supply set to 14.7 volts. We're getting 14.3 out of the speed controller. We're now reading 100% on there, and we are drawing 3.06 amps. We can then switch the speed. Well, we can switch it off. That's off. Now, in the off position, the speed controller fan continues running. So I don't really know why it does, because it's completely off now. There's no voltage coming out of here. We're back down to 120 milliamps. And if we go the other direction, there we go. Okay. So what I think would be a nice feature is if when you were switching from full forward to full reverse, you essentially you go from full forward to off, and then rather than applying full reverse current, you essentially ramp up slowly. So otherwise you're essentially going through the motor stall current as you transition from forward to reverse, and that's going to put additional load on the relays and the MOSFETs, which you don't really want. So I think maybe the last thing to test, but anyway, I don't think this does that, which is, I don't know, that's just the way it is. In the features list it says that it's got stall protection, so we can test that. We can see whether it really does by essentially shorting it out. Now, I had a really small wire here for testing a short with. So obviously that motor that I was using there is not capable of drawing 60 amps, it's not big enough. So I'll have to, I'm going to try this and see how it goes, and I'll report back. But otherwise I would say that in general, although it may not be capable of a full 60 amp or even 40 amp continuous duty, actually the quality of it is really not bad. So I'm sure that if you needed something that had these features and you wanted to run it at 20 or maybe 30 amps, it would probably do that all day long. I'm hoping I'll be proven wrong, but I'm not entirely convinced. Okay, so this is right now in 100% go, 100% full speed, and what we're going to do is get the multimeter on it, and we're going to measure the output, and we're going to see what happens to the speed controller when we go full. So what I'm going to actually do is reduce this down to 0. So that's now reading, that's now reading 0. And I'm going to switch this to forward. Right. Power supply is drawing a little bit more current, but I think that's just the relay coils. And then as I increase this, what I expect to see is the voltage go up ever so slightly. You can actually hear something whining. I can hear it anyway. Alright, okay, that goes straight to current trip. So the power supply is going to current trip, and the voltage drops to 10 volts, and I think that's the point at which the whole thing disables, unfortunately. So because the power supply is not able to provide the current, I don't think we're going to be able to do this test. I mean, it's interesting because at that point, yeah, we're only drawing. Okay, at that point we're drawing. Well, we're getting smoke. So we're supplying enough current. We're supplying 2 amps into that small wire, and our MOSFETs are actually starting to get a little bit toasty. Oh, yeah, diode's really hot. Let's turn this off. Okay, we get a bit of smoke there. But now the diode there, that's warm. I'd say that's a good 40-50 degrees. That MOSFET, these MOSFETs were in the airflow. That one's getting warm, 20 degrees maybe, something, I don't know, 30 degrees. Yeah. So that was getting them warm, but it didn't trip out. So what I was expecting is that maybe if we shorted this, the system would be able to detect the current. I mean, the current was only 4 amps, so I guess it's not going to kill it. Yeah, interesting. So I think if you manage to draw 100 amps through there and install it, or over 60 amps, I don't know. I don't see how it's going to protect itself. There is one way, so let's just turn this off. Now, the proper way that it could protect itself is with essentially a current measuring device. So if it was capable of measuring the current that's flowing through the output or the input stage, then it would be able to turn off if you had too much current flow. Yeah, so the whole PCB is pretty warm. Even the traces there. Yeah. And that's only 4 amps. Doesn't bode well. So there could be a shunt resistor somewhere across here, and then it's measuring the voltage drop across the shunt resistor, and that would tell you the current flowing through the output, and then it would be able to feed that current into maybe the microcontroller, and that would be able to switch, say, the relays off or the outputs. Now, does it have that? There's probably some ways to test it. I'm not sure. Is there? I don't know, can't think of a good way. But typically what you'd see is a really big resistor on the board between, say, like that's the ground plane and that's probably the power or output plane. So you'd see a big resistor on there, and then the microcontroller connected up to it. But I can't see that on here, so I'm not convinced that that is the case. There's actually a spare header there. Don't know what that would be for. Probably programming one of the chips. Well, that one's the only one that would be programmable. So there we go. So yeah, don't hold out a great deal of hope there for it dealing with 60 amps, but I guess we'll try it and see.